Hello, this is Alex, and today I would like to solve a very interesting GRE problem. How many positive integers less than 10,000 are there in which the sum of digits equals 5? I'm going to show two solutions of this problem. One is more intuitive in my opinion, but requires a little bit more calculations. The other one is very creative, but in my opinion hard to come up with on the spot. So let's jump right to it. One note before we begin is this particular problem, it's easier to consider a number like 0005, a four-digit number, versus deal with 1, 2, and 3-digit numbers individually. It doesn't make a difference, but it just makes the calculation slightly easier. So that's what we're gonna assume. So if we want to have a number which has sum of the digits equal to 5, we have a couple different options. So let's just try to write them down in terms of four-digit combinations. So first we can start with 5 and 3 zeros. Then we can start with 4, 1, and 2 zeros. Again, we're going to count the number of computations here of unique combinations. So this is just one example. Then we can have 3, 2, 0, 0. We can have 3, 1, 1, 0. We can have 2, 2, 1, 0. We can have 2, 1, 1, 1. Notice we cannot have 5 ones because that number would be greater than 10,000. So then the question becomes, okay, how many different four-digit combinations can we write with 5 and 3 zeros? And I think this triggers a slightly longer discussion. In any case, right, if we have four unique numbers, A, B, C, D, or letters, how many different combinations are there? And I really like to talk it out because, of course, yeah, many of you know right away the answer is 4 factorial, right? But just to understand it, you can say, okay, in how many ways you can fill the first blank, right? And you're going to say, well, in 4 ways. And then after you filled it, you have only 3 numbers left, right? Because you used one of them, then you have 2 left, and then you have 1 left, right? So you say, okay, it's 4 factorial. But then the question would be, okay, what if you had A, B, C, D, right? What would it be then? And then it's actually very similar, but you have to divide out the duplicate solution. Sorry, forgot about the D. So in this case, you in a way imagine that you still have 4 ways to populate the first one, 3 for the second one, 2 and 1, but then you actually divide it out by 2 factorial because your A1 and A2 are in reality the same thing. And then you can follow the example. If you had 3 A's and a B, again, it would be 4 factorial divided by 3 factorial. And then an alternative example, AA, BB, the answer would be 4 factorial divided by 2 factorial times 2 factorial. So this is a basic rules how you can solve those types of problems. So you always imagine you're giving them like indexes, where in reality, of course, they're just the same letter, and then you divide out by all the possible combinations of those A1, A2, A3. So coming back to this problem, here we know we can write this based on what we just discussed as 4 factorial divided by 3 factorial, which is just 4. And people can write it as 4 combination 3. Here you're going to have 4 factorial divided by 2 factorial, because again we're looking at the zeros which are appearing multiple times, and this is, I believe, 12. Here, same thing, 4 factorial divided by 2 factorial, which is 12. Here, same thing, but in this case the ones are repeating instead of the zeros, so this is again 12. Here it's the same thing because the 2's are repeating. So again, it's 4 factorial divided by 2 factorial, so you have 12 again. And here you have 3 digits repeating, so it's the same as the example, as the first example, so this is just 4. So when you sum all those up, you get, this is 48 plus 8, so you get 56, which is one of the options. There's actually an alternative solution to this problem. I saw it on the forum written by Zarathilab, and I think it's a very good creative solution, and I'm going to do my best to explain it here. The idea is this. We know that we are dealing with a 4-digit number since it has to be smaller than 10,000. So the solution assumes that we're going to put 3 dividers and then start, and as a result create 4 buckets. So you can see here we created 4 separate spaces, and now they're assuming we're going to be placing 5 coins or 5 balls in any order into those spaces. So they're saying that this redefines our problem, and those spaces will represent digits. So let's give an example of what I'm talking about. Let's start putting letter D's, which they will represent an individual coin of value 1. And let's put 5 of them randomly in here, right? So what number would this represent? It would represent 1, 2, 2, 0. So in this case, this is indeed a 4-digit number, which has a sum of digits equal to 5. So let's try a different combination. Well, let's put nothing at the beginning, so this would be nothing. Then let's put DDD, DD, right? What would this represent? This would represent a number 0, 3, 0, 2, which again is a number smaller than 10,000 with a sum of digits equal to 5. So as you can see, in this way, the dividers are separating the space so that we have 4 separate spots, right? Sometimes we can have nothing inside of them. Sometimes we can have 1, 2, 3, or 4 point values in there. And they're saying this represents all possible solutions to this problem. And this actually makes sense because you only have 5 Ds to place and 4 spots to place them. So this indeed does represent all possible solutions. So then the question becomes how you can assign how many different combinations are there of 5 Ds, 3, 4, 5, and 3 Ls or 3 dividers. And we can totally apply what we learned in the previous from the previous solution here, right? We know we have 8 possible choices, right? So we would say, okay, how many different combinations are there? So let's imagine we're assigning the indexes here, right? Just temporarily 3, 4, 5, and then 1, 2, 3, right? So it's okay, it's 8 factorial, but now we have to divide it out because we know that 5Ds, they actually don't have indexes in reality, so there are 5 factorial ways to arrange them, and then 3 factorial for the Ls. And you know, we can also write it out as 8C5. So how many 5-digit combinations are there out of 8? So so moving forward, we can calculate this out. So this will cancel with this, leaving us with 6 times, oops, I'm running out of space here. Let's continue here. So it's going to be 6 times 7 times 8 divided by 3 factorial, which is 6. This divides out and it's 56. Right, so we reach the same solution as last time, but in a significantly simpler way. And this is, like I said, a great solution. It is more visual, and yeah, if you can spot that, good for you. Congratulations. Finally, you can generalize the solution. You're going to use the number of dividers is going to be your number of digits minus 1, and the number b is going to be the desired sum, and that's your other number. And then your number of integers that you can make is going to be the number of combinations of a or b, actually it doesn't matter, out of the a plus b. So an alternative example would be how many 7-digit numbers can you create which have a sum equal to 7. So first your number of dividers will equal to 6, which is graphically represented here as about creating 7 spaces for you to place 7 Ds however you want. That's why B is equal to 7. So then we're looking at the number of 6 element combinations out of 13. So this will equal 13 factorial divided by 7 factorial times 6 factorial, which is a lot. Yeah, thank you.